All right, we are going to briefly touch on chapter 14. And this is all about solutions. I worked with a guy one time at Shasta College. He always wore funny t-shirts. And one of them said, "Have a problem? Chemists have the solutions." Okay, another bad joke. So the whole thing about solutions, first off, what is a solution? Well, it's just a homogeneous or homogeneous mixture. It's the same throughout. If you think way back to when we did lab, in the beginning of the semester, the first 2/3 of the semester, all the solutions you used were homogeneous. They were just the same throughout. There was no solids in them. There was nothing floating on the surface, hopefully. And that's what a solution is, a homogeneous mixture. We can have lots of different solutions, like your soda is a solution of sugar in water. It's also a solution of carbon dioxide in water. So there's lots of different ways to make a solution. I'm just going to touch very briefly on it, but the one thing I want to say, or one thing I want to touch on, is that like dissolves like. Like dissolves like. What does that mean? Well, polar dissolves polar. And nonpolar dissolves nonpolar. Okay, so let's talk about that real quick. And let me give you an example. Which is more soluble in water? And that's a weird way to spell water. There we go. And let me give you two molecules. One, ethanol. Let's draw the Lewis structure. 2 carbons. And an OH. And the other structure, hexane. 6 carbons. 1, 2, 3, 4, 5, 6, and enough hydrogen so that everybody has 4 bonds. We'll get there someday. All right. So which one of these is more soluble in water? Well, which one's polar? This is polar. This is nonpolar. Let's look at a water molecule. Uh-oh. What can these two guys do? Hydrogen bond. Okay, that is a hydrogen bond. And we can also have an H bond like this. So I know we've done hydrogen bonding between water molecules, but we've never done it between molecules that weren't the same. But we can still have hydrogen bond. There we go. We can still have hydrogen bonding going on there. So ethanol is more soluble in water than hexane. This is ethanol. This is hexane, hex meaning 6 carbons. The hexane is not soluble in water to any appreciable degree, okay? Because there's no place for it to interact with the water molecule. It's a nonpolar hydrocarbon. Well, guess what else is a nonpolar hydrocarbon? Okay, grease and fat. Grease/fat/oil. Those are, I'm going to just approximate it, they're just long hydrocarbon chains, okay? They might have something else on the end. fats that we eat, they do not look exactly like this, but this gets the point home. I don't know why I'm filling in all these hydrogens, just to waste your time, I guess. But here's a fat or a grease molecule, or an oil molecule. You know, you might have been working on your car, you might have olive oil in your hands. It doesn't much matter. Those are all hydrocarbons, okay? Why can't you just go to the faucet and wash off the grease or the fat? Because there was no place for the water molecule to interact with this fat molecule. So what do you use? Soap. Okay, and the very basic soap molecule looks exactly like that, but what I'm going to do is I'm going to draw it just as a jagged line. I'm going to draw a carbon, double bonded oxygen, single bonded oxygen, and that oxygen there has a negative charge. Well, what is all this portion? Well, there's a carbon there, carbon there. Everywhere there's a bend or an end, there's a carbon, and enough enough hydrogens to make 4 bonds. So this molecule up top, the grease or fat molecule, would look like this to an organic chemist, okay, or to a chemist. So everywhere there's a bend or an end is a carbon. It's just a quicker way to write carbons, because when you get to organic chemistry, you'll find out that it gets really tedious to write carbon over and over and over again. So what does that mean? Well, that means there's 2 halves to this molecule. There's this half, and then there's this half, which isn't really half, but we have what we call the hydrophobic or water-hating, and it's non-polar. And then we have the hydrophilic, and or water-loving. Okay, so this molecule has 2 ends. One end hates water, one end likes water. So what happens if you have a big glob of grease on your hand? So here's a glob of grease. Well, what happens is this molecule attaches itself so that the water-hating end is inside the grease molecule. And then, I didn't do it in the right colors, but that's okay. And then this water-loving end, looks like a little cactus with a flower. This water-loving end is on the outside. And then along comes the water molecules. Jiminy Christmas, what did I just do? You saw on my email. Okay, the water molecules come along. Remember, we can just draw them like little arrows. And they can interact with this, and they can wash away the grease molecule. That's how soap works. Like dissolves like. And we can make molecules. This is a very simple soap molecule. They get much more complex. This is how they actually used to make it in the olden days, when they'd use lard or rendered fat to make soap. It's called lye soap. Anyway, well, what about a practical application for this? Anybody like salad? You should. It's delicious. I'm sure you could probably buy salad dressing in a bottle. Let me tell you how to make it. Okay, let's take about 1 cup, and you can scale this recipe, 1 cup of extra virgin olive oil. Guess what? Extra virgin olive oil is hydrophobic. It won't mix with the water. And what water are we going to put in there? We're going to put in about 1/3 of a cup. I know these aren't milliliters, who cares? 1/3 of a cup of your favorite vinegar. And you can change it up. You can use balsamic, you can use red wine, whatever you want. My wife likes balsamic. I like red wine, so I make balsamic. And then, of course, every recipe you needs salt and pepper to taste. Remember, it's easy to add a little bit more, hard to take it out. And now we need something to make you know if you put oil and vinegar together and put it in a jar and shake it, it'll just separate out. We need something to make it stick together, okay? You can use lots of different things. I know some of you out there are thinking, oh, soap. No, don't put soap in your salad dressing. That's disgusting. Hydrophilic. In class, usually some guy says soap, and I tell all the ladies, if he invites you to dinner, don't go, okay? Anyway, what I like to use is 1 to 2 tablespoons, and again, this kind of depends on your taste, tablespoons of Dijon, and you do not need to measure any of this exactly, Dijon mustard. Not yellow mustard, okay, then your salad will taste like a hot dog. And you just put this in a jar and shake it. And use what you need. You'll see it gets really thick and kind of creamy-ish. And when you're done, put the cap on, put it back in the fridge, take it out a few minutes early so the olive oil will melt because it'll turn solid in the refrigerator. And then you have salad dressing. It takes you 5 minutes to make, less, and you can use it all week long. You don't have to buy it, okay? What else could you use besides Dijon mustard? You can use, if you put it in a blender, blend with really any fruit or vegetable puree will do this. So raspberries will work. Avocado. And it doesn't take much. If you're vegan, something that's really common is raw cashews. Okay, there are things in the Dijon mustard and all of the, well, this part is so you could substitute it out if you don't like the mustard or want to make something different, okay? I should put and you have to kind of put these in the blender. They won't shake up as easily. But they all contain molecules that are similar in structure to soap, and they will bind the oil and the vinegar together, and you'll have a nice salad dressing. Okay, that's it for this video.